You've probably been in this exact meeting. You spend months training a model, tuning hyperparameters, squeezing out like a 99% accuracy rate.
So yeah, we've all been there.
Right. And you walk into the stakeholder presentation,
Yeah.
hand over the results, and the chief medical officer or, the VP of finance looks at it and asks, okay, but why did it make this specific prediction right here?
And that is exactly where it all falls apart.
Exactly. You hesitate, you mumble something about high-dimensional vector spaces, and you just watch their trust in your model instantly evaporate.
Yeah, I mean, it is basically the defining bottleneck of modern data science right now. We deploy these massive deep learning neural networks that operate as brilliant, highly capable, but complete black boxes.
Yeah, a total black box.
Right. They can find invisible statistical correlations across billions of parameters, but they are fundamentally incapable of articulating their own reasoning.
Which is why today's deep dive is just so critical for anyone building or deploying models. We are unpacking the frontier of AI architecture that's designed specifically to solve this explainability crisis.
It's a really exciting space.
There really is. The sources today, we've got a technical presentation, a system READE file, and a recorded platform demonstration. And they all detail the HumAIne NSAI platform. And NSAI stands for Neuro-Symbolic AI.
So the core promise of this architecture is giving domain experts, like people who don't necessarily write Python every day, giving them the ability to inject their own hard-earned logical rules directly into the neural network's training process.
Yeah, so if you are a data scientist fighting the black box problem, or you're just insanely curious about where AI is heading, we're going to break down how we are finally combining raw data crunching with actual human reasoning.
Let's get into it.
So let's start with the theoretical foundation. Because before we look at the platform itself, we need to understand the philosophy here. To understand Neuro-Symbolic AI, our sources frame it around Daniel Kahneman's System 1 and System 2 thinking concept.
Right, but applied strictly to computational systems.
Exactly. So can you break that down for us?
Yeah, so System 1, in the context of an AI architecture, is your standard machine learning stack. These are differentiable, continuous mathematical operations.
Like your basic neural nets.
Right. A neural network ingesting millions of pixels or like audio waveforms to find statistical patterns, that operates entirely as System 1. It's fast, it's intuitive perception, but it has absolutely no capacity for deliberative logic.
No multi-step reasoning.
Exactly. So then System 2 is the discrete programmatic side. We're talking about knowledge graphs, relational databases, explicit if-then rules, classical symbolic logic.
It's deliberate, it's explainable, and it's very rigid.
Exactly. And the goal of Neuro-Symbolic AI is to fuse that differentiable learning with discrete logic. And the literature actually outlines two primary paradigms to achieve this. You have learning for reasoning and reasoning for learning.
Okay, let's unpack this. What's the difference?
So in the learning for reasoning pipeline, the neural network basically sits at the front of the architecture. It acts as a perceptual filter.
So it processes the raw data first.
Right. You feed it a chaotic, high-dimensional environment like maybe a live video feed, and it translates that raw data into structured symbols or objects. And then those objects are passed into a symbolic reasoning engine that handles the actual decision-making.
Okay, so the neural net handles perception, and the symbolic engine handles logic.
Exactly. But the alternative is reasoning for learning, which completely flips the architecture. Here, you place the symbolic logic over the neural network to basically constrain its learning phase.
Wait, okay, let me throw an analogy at you to see if I'm parsing this right. Is reasoning for learning basically like giving a race car, the neural network, a set of guardrails, which would be the symbolic rules, so it doesn't fly off the track?
That's a perfect way to look at it, yeah.
It sounds a lot like a physics-informed neural network, right? Where you inject the laws of thermodynamics into the loss function. The network is still learning on its own, but those physical laws act as a mathematical penalty.
Right, so it doesn't hallucinate impossible physics.
Exactly. Are we basically just replacing the laws of physics with human business logic?
That maps perfectly. Instead of the Navier-Stokes equations governing fluid dynamics, you are injecting domain-specific heuristics. So like a doctor's diagnostic criteria or a compliance officer's regulatory framework becomes a quantifiable constraint on the model's loss landscape.
Okay, I have to challenge the utility of doing that, though. Because, the entire paradigm shift of deep learning over the last decade was moving away from feature engineering and hard-coded rules.
That's true.
We learned that if you give it enough data, a neural network will discover n-dimensional patterns that human experts are completely blind to. So if we force a network to adhere to our pre-existing low-dimensional logic, aren't we just handicapping its performance?
Well, what's fascinating here is that the sources actually anticipate that exact criticism. The HumAIne platform, it doesn't enforce these rules to limit the model's ceiling, It enforces them to raise the model's floor,
Raise the floor, meaning what exactly?
primarily through sample efficiency. If you encode an undeniable truth about a domain directly into the architecture, the model doesn't have to burn thousands of epochs and massive compute resources attempting to infer that truth from noisy data.
Oh, I see. It already knows the basics.
Right. It anchors the model, which makes it drastically more robust against adversarial inputs or out-of-distribution shifts. Plus, obviously, the explainability factor is huge.
Yeah, I buy the theoretical benefit for sure.
Mm.
But the friction point is always the implementation. Bridging continuous vector spaces and discrete logical rules is notoriously difficult.
Very difficult.
If you look at the mechanics of the HumAIne platform, the engineering challenge is pretty immediate. You cannot apply a discrete logic rule like if clump thickness is greater than 4.0 to a raw matrix of image pixels.
No, the model has no innate concept of what clump thickness represents geometrically.
Right. So having established why we want to combine logic and learning, how does the platform actually ingest unstructured data to make this possible?
Well, the platform solution to this bottleneck is basically acting as a universal semantic translator. Before any rules are applied, it forces all that unstructured data through a pipeline that extracts Boolean semantic tags.
Okay, let's trace the data flow for an image dataset. The RayDME file outlines a scenario where a user uploads a ZIP file containing brain tumor MRIs.
Right. Standard medical imaging.
And the system doesn't just flatten the images and feed them to a convolutional neural network. It actually runs two parallel extraction processes. The first utilizes classical mathematical statistics to pull texture features.
Yeah, specifically, it computes a gray-level co-occurrence matrix, or GLCM.
A GLCM. Okay.
Which is a deterministic algorithm that measures the spatial relationship of pixels to calculate attributes like contrast, homogeneity, and energy. It basically quantifies the texture of the tumor.
Okay, but that handles the mathematical properties. It still lacks semantic meaning, right?
Exactly. And this is where they introduce an external API. The HumAIne platform calls the OpenAI Vision API, and it passes the medical images to a large language model with vision capabilities.
Oh, wow.
Yeah, it prompts the model to generate semantic tags. So it outputs a matrix of true and false columns, attaching tags like, has the irregular border or high contrast region to each specific patient's scan.
And they do something similar for text data, right? Like if you upload a massive CSV containing SMS messages for a spam filtering model.
Right. The platform batches the data. The documentation specifies batches of 5 to 250 rows at a time and sends it to the OpenAI text API.
So the LLM parses the natural language and extracts discriminative Boolean tags, like contains link or urgent tone.
You got it.
Okay, but wait. If the platform relies on an LLM to generate these Boolean column tags, sending batches of up to 250 text messages to an LLM raises a huge red flag for me regarding API drift and hallucination.
Yeah, the consistency issue.
Exactly. Generative models are non-deterministic. If I run 10,000 images through the Vision API, the LLM isn't going to strictly stick to the exact tag has irregular border. It's going to spit out 50 different ways to say the same thing.
It'll say border is irregular, jagged edges.
Yeah, asymmetrical boundary. Doesn't that create a messy data set? You're going to end up with a brutally sparse matrix containing thousands of redundant overlapping columns.
And a completely sparse matrix would totally shatter the downstream training process. But the HumAIne platform documentation details an automated reconciliation step to prevent this.
Oh, really? How does it fix it?
It takes all of the generated tags and maps them into an embedding space to calculate semantic similarity.
Okay, clever.
Yeah, using vector distance, it clusters those overlapping variations, so your jagged edges and your irregular border, and it just collapses them into a single unified column.
So it's essentially performing automated dimensionality reduction on the LLM's outputs before it ever reaches the primary model.
Exactly. The result is a highly structured, clean, tabular data set where every single column represents a human-readable concept.
Okay, so now that the raw data is neatly translated into tags and tabular features, how do we actually apply human logic to it?
Once the data is in this tabular format, the domain expert interacts with the platform's no-code interface. This is where we get into defining what they call predicates.
Right, so a doctor who maybe has zero programming background can look at the GLCM data column for, say, clump thickness and create a predicate named high clump thickness.
Setting a threshold, yeah.
Exactly. Establishing that any value over 4.1 triggers the predicate to true.
And those predicates act as the building blocks for the logical rules. The user interface allows them to stitch these predicates together using just natural language.
Which is a brilliant UI feature.
Yeah.
They simply type something like, if high clump thickness and high mitosis, then malignant.
It's that easy. And under the hood, the platform captures that natural language string and uses an LLM to parse it into strict mathematical syntax. Specifically, it compiles it into logic tensor network axioms, or LTN axioms. And this is really the heavy lifting of the platform, because when the user hits train, the system orchestrates this sort of showdown.
A showdown between models.
Yeah, it simultaneously trains 3 distinct models: an MLP, a rules-only model, and the LTN.
Let's define the architecture of those 3 competitors to really understand what's happening. So the MLP, the multi-layer perceptron, that serves as the baseline, right?
Right. It's a standard neural network that trains exclusively on the tabular data and those semantic tags. It remains completely blind to the logical rules the doctor typed into the UI.
Pure data, no rules. It's just pattern recognition.
Yep.
And the second competitor is the exact opposite, the rules-only model.
Yeah.
Pure logical reasoning. It contains no learned weights, no backpropagation. It operates as a rigid, hard-coded decision tree.
Right, built entirely from the user's logic. If a patient's data perfectly satisfies the if-then rule, it assigns a diagnosis. But if the data falls outside the bounds of the rule, it has no fallback mechanism. It just guesses randomly.
So it's very brittle.
Extremely brittle. Which brings us to the third model, the logic tensor network, the LTN. This is the hybrid.
Hybrid, okay.
It's a neural network, but its loss function is integrated with the user's axioms. During backpropagation, the model evaluates how well its current weights satisfy the logical rules across the data.
So it's basically penalized for violating the expert's logic, while simultaneously rewarded for finding statistical patterns in the raw data.
Exactly.
Here's where it gets really interesting. Think about these 3 approaches like students taking a test.
Oh, I like that analogy.
The MLP is the student who just relied on pattern recognition from old tests. The rules-only student is the one who memorized a few flashcards but blanks on literally anything else. And the LTN student actually studied the patterns. A&D understands the core principles.
That's a perfect way to visualize it. And to test that architectural theory against empirical data, the sources detail a real-world pilot study utilizing the Wisconsin breast cancer dataset.
Which is a classic tabular dataset.
A total classic. The domain expert utilized the platform to encode specific diagnostic rules. So something like, if your clump thickness 4.1 and uniformity of cell shape 3.0, then malignant.
And they ran the 3-way training pipeline. What were the results?
The LTN demonstrated a clear performance advantage over the pure MLP. Top-line accuracy bumped up from 91% to 92.7%.
Nice. But accuracy isn't everything. What about the secondary indicators?
Right, and that's the compelling part. The LTN achieved higher F1, precision, and recall scores, which indicates a much more robust boundary between classes.
But didn't the demonstration video highlight a specific edge case? Something about the LTN predicting differently than the explicit rule.
Yes, and this perfectly illustrates why the LTN outperformed the others. They isolated a specific patient record where the domain expert's hard-coded rule was empirically incorrect.
Wait, the expert's rule was wrong.
Right. The rule predicted a malignant tumor, but the biopsy confirmed it was actually benign.
So the rules-only model naturally failed this case because it blindly executed the flawed instruction.
Exactly. But the LTN, which was explicitly trained to follow that same rule, actually got the prediction right. It successfully predicted the tumor was benign.
Okay, wait. If the LTN's loss function penalizes rule violations, how does it learn to just ignore the rule?
Because of fuzzy logic?
Fuzzy logic.
Yeah, the mathematical foundation of a logic tensor network relies on fuzzy logic. The axioms are not discrete, binary commands that break the gradient. They are mapped using what's called T-norms.
Okay.
This translates Boolean operators like AND and OR into differentiable real-valued functions. So the rules exert a gravitational pull, but they aren't absolute constraints. They allow for exceptions.
So in this specific patient's case, the neural network component detected overwhelming statistical evidence in the other features indicating the tumor was benign.
Right. The empirical gradient basically overpowered the logical penalty.
Oh, wow. So the model learned the nuance of the domain. It learned that the expert's rule is generally a fantastic heuristic, but it also learned exactly when the messy real-world data contradicts the rule.
It handles the messiness of real-world biology without catastrophically failing.
That is incredible. And that capability extends beyond structured medical data, right? The sources detail a second deployment focusing on SMS text spam filtering.
Yep, using the text data we discussed earlier where the OpenAI API extracted tags like contains link, urgent tone, and prize claim from raw text messages.
Right. And in the platform, the user can layer those predicates to build more complex abstractions, right?
Yes, the documentation calls these composite predicates. So a user can define a new concept, let's say, is promotional, and mathematically define it as any row where both contain slink and prize claim are true.
So it creates a hierarchical logic structure.
Mm.
And then the user's final top-level rule becomes incredibly simple to read. Just something like, if it's promotional and urgent tone, then spam.
And the LLM translates that down through all the composite layers, compiling it into a dense matrix of T-norms that the LTN can use during backpropagation.
Okay, so we've got this highly accurate rule-guided model. But let's bring it back to the beginning. The whole reason a data science team would migrate to an LTN platform instead of just deploying an MLP is explainability, right?
Absolutely. It's centralized in the application's Explain tab. This is their implementation of explainable AI, or XAI, and it completely resolves the black box problem we discussed at the start.
So how does it actually explain itself to the user?
Well, when you query the trained model with a new data point, it provides a comprehensive diagnostic readout. The first layer of that readout is a SHAP decision plot.
Okay, SHAP values. So it utilizes game theory to calculate the marginal contribution of every single feature to the final prediction. You get a visual plot showing exactly how much the clumsicness or the urgent tone pushed the model's output probability.
Right, so that visualizes the statistical mechanics, but the second layer of the readout bridges the gap to human reasoning. The platform identifies and displays the exact logical rules that were triggered or violated by this specific data point.
So you can see if the model followed your advice or ignored it because of that fuzzy logic.
Exactly. And the third layer is what you actually hand to the stakeholder.
The magic bullet.
Yeah, the platform utilizes retrieval augmented generation, RAG, to synthesize everything. It feeds the SHAP values, the triggered rules, and the original dataset's domain context into an LLM.
Oh, wow. So the output is just a natural language paragraph that explains the diagnosis in plain English.
Yep, citing both the statistical feature importance and the domain expert's own encoded logic.
So what does this all mean for you, the listener? It means you are no longer asking an executive to trust a mathematical abstraction. You are actually proving that the AI's internal architecture is validating and applying their specific domain expertise.
It bridges the gap perfectly.
It really does. So to summarize our deep dive,
Yeah.
we went from Kahneman System 1 and 2 to analyzing how the HumAIne platform translates unstructured images and text into semantic tags using LLMs.
Then we examined how those tags feed into logic tensor networks.
Right, utilizing fuzzy logic to mathematically integrate human reasoning directly into a neural network, culminating in a model that gives us superior sample efficiency, robustness, and true explainability.
It's a huge step forward. The platform successfully establishes a bidirectional interface between human reasoning and high-dimensional computation. But, this capability forces an unavoidable epistemic problem.
Uh-oh, what's the problem?
Well, think about it. The HumAIne platform proves we can effectively encode human expertise into neural networks. But if the architecture is designed so seamlessly that any domain expert can inject rules that shape the AI's behavior, what happens when two leading experts input slightly conflicting rules into the same model?
Oh, wow. I didn't even think of that.
Right. In the quest to make AI more human, we might just end up mathematically encoding our own subjective biases. When the experts disagree, which truth will the machine ultimately learn?
I'll leave you to mull that one over. Thanks for joining us on this deep dive.